Okay, so to dive right in, what is a set? A set is basically just a collection of objects. It can be infinite or it can be finite. In math, we're pretty used to dealing with sets in terms of things like uh, intervals, right? So if we've got -3 to 4, that's a set. Negative infinity to 0, that's a set. This is the set of negative real numbers right here. Negative infinity to infinity. Or this is just the real numbers, which we'll normally write looking something like that. And then we've got the set of integers, which we write as a z. We've got the set of natural numbers, which are basically, it's the positive integers, sometimes including 0, sometimes not. You can usually figure out by the context. And also something like 8 to 15, something like that. These are very common sets for us to deal with in math. Sometimes you'll also get the set of answers to, say, x squared is equal to 4. The set of answers for that is -2 and 2, which gets us into our next thing, set builder notation. That's basically when we have these brackets and then something in the middle. And this is one way that we have to write a set. And if we were to want to write the integers as a set using set builder notation, the reason it's z is comes from the German for number, Zahlen. So this would be -2, 0, 1, 2. The natural numbers, if we're including 0, look like this. Okay. We can also just come up with sets like we're going to use later. Let's say I want to go to the grocery store and I want to get eggs, bacon, and milk. This is a set that is less mathematical, but it's a set nonetheless. So element of, so 1 is an element of the integers. And we write it using this. That's a terrible version of it, but we write it using something like this. It looks kind of like a lowercase e. So if I want to look at this setup here, I want to say 0 is an element of, that's much better, -3 to 4. But 8 is not an element of -3 to 4. So if we want to say something is not an element of, we put that little strike through the center of it. And that just means that it's not in this particular collection of objects. Pi is not an element of z, but pi is an element of r. And also notice that these guys can be infinite or finite. We're gonna deal with both a lot. Obviously, there are infinitely many real numbers. There is infinitely many negative numbers. There's infinitely many numbers between -3 and 4. Infinitely many integers and natural numbers, but only finitely many solutions to x squared is equal to 4. Only finitely many things on my grocery list. So there's a few different things that we might be interested in asking relating to sets. One of them being, is one set a subset of the other one? So let's say me and my roommate both want to go to the grocery store, and I want to get eggs, bacon, and milk, and he wants to get eggs. My list to his list is eggs, milk, bacon, and bread. So we can ask, is one of these guys a subset of the other one? And the answer is yes, because everything that's in my list, or that's on my grocery list, is also in his grocery list. And notice that for me, bacon comes before milk. For him, milk comes before bacon. That doesn't matter. These lists are not ordered objects, or these sets are not ordered objects, even if your list has an order. So that means that my list is a subset of his list. So it also is a proper subset. So if we have this thing that looks kind of like a stretched out C, without the underline, that means that it's a proper subset. That means that his list is actually includes things that are not on my list. But this underline means it's basically less than or equal to versus strictly less than. So another example would be the natural numbers are a subset of the integers, and the integers are a subset of the real numbers. And I'm usually going to write it with this underline, but these guys are all proper subsets. So one way that we can write this, one way we can determine, the normal way that we will determine if two sets are equivalent is if I have two numbers, A and B, and I know that A is greater than or equal to B, and A is less than or equal to B, that tells me that A is equal to B. It's going to be the same basic idea for the natural number, or for proving equivalence of sets. So if I wanted to look at, let's assume that so if I have A is a subset of B and B is a subset of A, then I have A is equal to B. And this raises a pretty natural question of how do I show that one set is a subset of another one, and that we're going to use something called the method of choice, and we're just going to show that for all x in A, x is an element of B. This is the same thing as saying that A is a subset of B. So if I want to look at, show that the positive integers are equal to the natural numbers without 0. There's no 0 in this list. Then I would say if X is an element of Z plus, then that basically, that means that it's looks like 1, 2, 3, 4, blah, 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 then X is an element of the naturals minus 0. And then the same thing if X is an element of the naturals minus 0, then X is an element of Z plus. This is a pretty trivial example, but this idea is going to be useful sometimes. Another very important set just looks like that. That's normally how we write it. Sometimes we write it like this. It's the empty set. It's a list that has nothing on it. It is a collection of no objects. It comes up a lot, and it is a subset of every single set. Also, so let's say we've got then we have the empty set is going to be a subset of both the set of A and the set of just B, and that's going to be the subset of AB. So we also know that the empty set is a subset of AB. The empty set is actually going to be a subset of every single set, but one thing that I want you guys to understand is that A is a subset of itself, which is why this whole thing works, and that we have transitivity on this. And I'll dive into transitivity a little bit more later, but basically it just means that if we have A is a subset of B is a subset of C, then A is also a subset of C. That it is a transitive relation. Okay, so continue on here. We're going to look at some set operations. So the union of two sets, A and B, this is the formal definition here, is a set that every element of A union B is either an element of A or an element of B. And every element of A or B is in A union B. So that would be a formal definition of A union B. To give you guys an example, if I have my grocery list of eggs, bacon, milk, union. Let's say I have my other roommate, eggs, bacon, and He's a degenerate, so he's having beer for breakfast. Then the new list would be eggs, or the union of these guys would be equal to the set eggs, bacon, beer, and milk. So this is an important thing here. There is no redundancy. Just because eggs and bacon appear on both lists does not mean that they appear twice. If we want to look at so also if A is a subset of B, then A union B is just going to be B. That's an important thing to note. Yeah. So one useful tool that we have for these guys, for analyzing these, is Venn diagrams. So if we've got the set A, the set B, then the union of these two sets is going to look just like this. So that comes in handy sometimes, being able to look at it. Although sometimes the pictures can be deceiving, because if A is a subset of B, then this whole area right here is empty. And what it actually looks like is something more like this. Pretend that doesn't exist there. So A, B, and it's just this whole area here. So keep that in mind. Venn diagrams are useful, but sometimes parts of them will be empty when we draw them. So intersection. To give you a formal definition, A intersect B is the set of elements such that if X is an element of A intersect B, then X is in A and X is in B. So it is precisely that collection of objects. So if we look at me and my degenerate roommate's breakfast again, then it would just be eggs and bacon. Would be the intersection of my list intersect roommate list. Cool. So what does the Venn diagram for this look like? It would be this right here. Another thing to note, if A is a subset of B, then A intersect B is going to be equal to A. And regardless, A intersect B, we can only lose elements for this. So it is always going to be a subset of A, and it's also going to be a subset of B. Similarly, up here, A union B is always going to be a superset of A, or so A is a subset of A or union B. It's the same thing. Superset is just the opposite. And B is also a subset of A union B. So set difference here. Is basically saying that it is the collection of objects x such that x is in A and x is not an element of B. So this guy comes up a bit less often than the other two. But if we want to look at, it still comes up pretty often, and actually it comes up most often in terms of the complement that we're about to see. But what does it look like? It looks, if this guy is A and this guy is B, it looks like this, and it does not cover this middle area. So complement in universe. So whenever we are dealing with sets, we're implicitly dealing with a specific universe. So if I want to say the complement is basically the universe minus, so a complement is the universe minus A. So if I'm dealing with a set, say 0 to 4 complement, the natural thing for me to assume is that my universe is R. So I'm actually looking at R minus 0 to 4, which is equal to, sorry, that's parentheses, negative infinity to 0, union 4 to infinity. Sometimes it's harder to tell what our universe is, but usually the context will be pretty clear. So if I want to say 1, 2, 3 complement, then it will be pretty clear whether I'm dealing with the naturals, the integers, or the real numbers, or even anything else that this is a subset of. But this is going to generally be pretty clear. So power set is going to be the last it's going to be the last set operation that we introduce here. So the power set is the collection, is the set of all subsets. So it's the set of all subsets of a set. So P of A, if A to AB, then P of A is the set of all subsets. So let's go through. First thing, we can't forget the null set. The empty set is important to make sure that gets on the list, and then the collection of all objects with only, or sets with only one object in them, and then all subsets with two objects in them. So this is the power set of A. And so the for your homework, you will be asked to do it for A, B, C, and one way that you will know that you did your list correctly is because so this guy has 2 objects in it, right? This guy has 4 objects in it. That's because the size of P of A is going to be equal to 2 to the size of A. And that's what this kind of like these absolute value bars mean. That's the size of, or the cardinality. The cardinality is just the way that for sets we say the number of elements in a set. And when we're dealing with finite things, it's pretty easy to see. But the formal definition is going to be based on mappings, because that covers our infinite set cases as well. So let's talk briefly about, let's briefly show how we know that this statement right here is true. So the collection of of subsets of A, for every single element, we can list these guys out. So we can say we've got a first element, a second element, all the way up to the nth element. And for each of these guys, there's 2 options. Either it can be included in the subset, or it can not be included in the subset. So, and that's going to define every single subset. So every single subset is going to be basically defined by, is the first one in it? Yes or no? Is the second one in it? Yes or no? Is the third one in it? Yes or no? And that's going to keep on going. All the way up until we get to the nth. And that's going to define every single one of our subsets. And if we want to look which one's the empty set, it's just we go all the way down this track of no's. What about if we want to look at the set itself as a subset? Then we go all the way down this track of yeses. So we capture every single one of our sets. And each time we're multiplying by 2, that means that we have 2 to the n possibilities. And n is equal to the cardinality of our set A. So we have the 2 to the cardinality of A possibility, or subsets of A, which means that the power set has 2 to the A elements, 2 to the A objects in it. No, not that. Cool.